All right. Welcome, everyone, to another seminar at the Wolfram Institute. So, today I'm delighted to introduce Tate Allen, who's going to be presenting a project and continuation of his work done at the summer school this past year in 2024 on finding a single axiom for rings and the mathematical structure, as you'll see. So, this is the familiar structure everyone knows from school, where you can add and multiply and yeah, so looking forward to this. This is a very good example of how the sort of meta mathematics branch of our work sort of extends in many possible directions. And I'm sure that we're going to see very good examples of that sort of philosophy today. And obviously, if there's algebra involved, I'm very happy and it's, very dear to my heart. And yeah, please take it away.
Thank you very much. All right, I'm gonna go ahead and share my screen now. Thanks for having me. So can you see it all right?
Yes, we can
Yeah.
see it.
All right, excellent. So as Carlos was saying, this is about finding a single axiom system and a minimal axiomatic system for rings. So in order to talk about ring axioms, we must first talk about axioms and rings. So first of all, the sort of purpose and inspiration behind this project was to replicate the work of both William McCune and his work into finding a single axiom for groups, which is another algebraic structure having four axioms, and Stephen Wolfram's work in Boolean logic, and he found a length 26 or 27 axiom for Boolean algebras that only use a single operator. So my project is aiming to do something similar with rings. Now, axioms are just the sort of bare bones statements of mathematics. They're the building blocks we build everything off of, and we can sort of say that they're statements so simple, we just accept them as true without proof because there's really no way to prove them. And rings are, as Carlos mentions, something you see in every algebra class. They're an algebraic structure satisfying the 7 axioms you see on screen. Mainly, that's their abelian groups with respect to their first operation, and that their second operation distributes over the first and is associative. All right, with that said, let's go into the actual work of the project. So what you see before you, this monstrous equation right here, is the prime candidates for a single axiom for rings that we have found so far. And I call it in the title Tarski's ring axiom because in a paper by a mathematician named George McNulty, he reviews the work of Alfred Tarski and his doctoral students in a conference in I believe the 1950s that sort of goes over the general equational theories of certain structures and their bounds and just their properties. And so one result is that any equational theory of groups and rings has a single or is bounded by the number of equations needed to contain all of the information. So through his proof of that very, very general statement, we were able to, and by we, I mean my mentors and I, were able to derive this axiom, which, as you can see on the slide, is 351 characters, not including the parentheses. And this sort of equational length that I've been mentioning is sort of the way that we define how good a single axiom system is. Because first and foremost, we want it to be short. And then second of all, we want to use as few variables as possible. And this tree down here is sort of just a nicer way of counting the elements rather than just going 1, 2, 3, 4, 5, 6, so on until you reach 351. And I'll go ahead and edit this here so that you can see exactly where all of the symbols end up. So I believe this y right here is the one at the very, very end of the equation.
So this encodes the parenthetic structure.
Yes, so parentheses are not included at all in the counting of this. And if you'll notice, I also in the axioms seen on the previous page, goodness. So these ones have these quantifiers as well. You have the for all ABC, for all A, for all whatever. Those are also omitted from the equational length. And this is just borrowing from the notation that McEwen used in his group axioms. So yeah, the short answer is parentheses aren't included.
Right.
You also have some additional definitions, like this -1 is not the.
Yeah.
So
Exactly.
Can I ask something quickly in that direction, or were you going to
Yes.
say something, Nick?
No, and well, the other thing I think the more standard way of counting it's just leaves, because you have a tree, right? You just the natural thing is just count how many leaves there are.
Mm-hmm.
Maybe the depth of the tree.
Mm-hmm.
Yeah. Yes.
So I see I believe three distinct binaries and one unary. Is that right?
Yes, that is correct. So as you have probably
Really?
surmised, this sort of circle minus is just the equivalent to adding the additive inverse. It's just another way of writing it. And if you look into the existing single axiom systems, like Stephen Wolfram's, for example, he uses NAND as his operator. And it turns out that it's relatively well known to be much more efficient to use things like division and subtraction in terms of single axiom systems, because they contain information of both multiplication and inversion, or subtraction, addition, inversion, excuse me. And so I omitted that from the presentation, but yes, this is exactly the inverse of the binary operation.
And the unary, the little bar.
Right. So the little bar is essentially the same thing. That's just the additive inverse of x. If we go back to those axioms right here, you can see a circle plus a bar is some identity element E. And so that's what that means. It's just, you can think of it like a naught.
Okay.
So in this case, I guess E would be is it the additive inverse?
Yes, it would be.
Or the additive identity element. So 0 in that case.
It would be 0, right? And for these standard 7 ring axioms, we don't necessarily know that there is a multiplicative identity.
Mm-hmm.
And so yeah, this
But
E is 0.
you have one, right? In that big expression, you have one.
Yes,
What?
well, that is, I'm glad you pointed that out, because this axiom only works when there is multiplicative identity. And I'm glad you pointed that out, because I failed to mention that. So pretty much for the rest of the presentation, we're going to be assuming that our rings do have a multiplicative identity element. I did do some work into finding minimal axiomatic systems for rings not having multiplicative identities. And according to Tarski's paper, it is possible, but I didn't actually find one.
And so here E is just a variable, and 0 and 1 are the constants, right?
Yeah, so yes, it's a notational inconsistency on my part, but yes, 1 is the multiplicative identity, 0 is the additive identity, and E is an element of the ring. All of the letters here are elements of the ring.
Uh-huh. So, right, and wouldn't, I mean, maybe I'm jumping ahead, but wouldn't the analog of the NAND axiom of Boolean logic, wouldn't the equivalent of that be some potentially higher arity single operation that somehow absorbs all this multiplicity of operations?
Yes, that's a really good point. I haven't really explored that very much, but as far as we know, like these are 2 abstract operators. We don't necessarily know how multiplication and addition are defined. They just have to satisfy certain properties. And so I guess one problem I run into when thinking about it that way is that in the case of, say, Boolean logic, you have that the operators are very well defined. If you have zeros and ones, you know how they're going to act with one another. But for all we know, multiplication doesn't necessarily work like it does in the real numbers. It can just be a function that sends everything to zero, for example, and it still satisfies all the axioms. And so it's a lot tougher to make a higher arity operation that combines these two when they're abstracted like this.
Yeah, yeah. My question is, I mean, I'm assuming that these binaries are just binaries, right? That they have no further axioms, and all you impose is this single axiom on all of them simultaneously, right?
Right.
Like, that's the magic of this. I mean, that's the punchline that I guess the audience should take away. That there are no axioms imposed on these binaries or unaries or constants, and out of these, it's possible to prove that you can actually derive all the usual ring axioms. Is that correct?
Right, it is. So one thing that, well, actually, I was going to talk about a bit later, but I'll talk about now is that I tried, so this is well known, or not well known, but it's proven in Tarski's paper that this is a result that does work both ways. Like this, you can encode all of the ring axiom information into this single axiom. But if you look into the standard ring axioms and you evaluate all of this just by hand or in Wolfram language, you eventually reach a tautology of just y equals y. And so at the very least, we can systematically prove in this specific case of unidal rings that it follows from the standard axioms.
Mm-hmm.
So you can derive the standard axioms for rings one at a time from this?
Supposedly.
By substituting in different variables for A, B, C, X, Y, Z, that kind of thing.
Right.
I imagine the trick would be to like set a lot of these things to zeros or ones, right?
Yes, it would be. But
no, that wouldn't be enough, right? Because you don't have an additional axiom that those identities act as identities.
Oh, that's true.
Right.
The only
And
thing
so
you're allowed to do is to take this giant piece and substitute it into itself.
mhm.
It's like very hard to imagine, but yeah.
No,
It's
Nick is
like
exactly right
unnecessarily.
about this.
Yeah.
Mhm.
So
It's supposed to be grow in size first in order to contract to an axiom. So it's kind of, yeah.
and
I
that's
think
why you see
Anyway, go. No, go.
that's why you see things like C minus C and X plus 0 and X times 1, because you can't just evaluate them. Like you
Sure.
know what they're going to be, but we don't actually have that information yet. And so as Nick said, it's pretty much one big substitution into itself until you can get something out of it. And apparently you can. I really tried to make a proof object in Wolfram language, wasn't able to do that, and it's a monumental task to try this by hand. So for now, we're going to have to settle for one direction. What was that?
Oh, what was the challenge with trying to do it, that proof axiom in Wolfram? You said you tried. What made it a challenge to not get right?
Well, I was getting a lot of failures, and I was getting a lot of just, I guess, exceptions. I don't really know how to call it.
Well, I wouldn't rely
like-
on automatic theorem provers to actually trying to prove, because this is a very giant axiom. It's like your tree search exploration gonna explode.
Yeah.
It's like even for the Wolfram axiom, which is like 10 times smaller than that, it's already problematic to prove anything from it automatically, right? So it's like the only way forward here is just to actually reverse engineer the original construction of this and somehow derive those.
Mhm.
Right. And in that vein, of a theme we're going to see here is that the scope of this project is very limited by hardware,
Mhm.
because the code ramps up very fast.
So, do you have? I mean, maybe you're gonna talk about this, and I should just let you go on. But how do we know this is true? that's kind of the
Well,
Yeah.
because George McCune, or not McCune, George McNulty, excuse me, proved it. That's why we know it's true. And I didn't put it in the presentation. There's a research paper on it that any equational theories satisfying such and such properties are able to be reduced into n number of axioms. And then he sort of explicit or generally writes out an axiom. And from that, we were able to sort of not copy paste per se, but to plug in the ring axioms and plug in what we have here. And it's a 4-page or 5-page long proof, I believe. And so I didn't really go through and sort of transcribe it into the presentation, but we know it's true
But-
because it's proven.
right,
pretty
right,
much.
right. So then, I mean, I imagine that it is proven somewhere. But my question was, if you have that proof, I mean, maybe that's what you use to kind of guide the search, right?
Well, yeah, and that is kind of what we're gonna see here, is that it's like, okay, well, we already have a single axiom, so what's the search for? Where do we go from here? And that's actually sort of the next thing I'll be talking about, because really this axiom just serves as an upper bound, right? It's massive. Surely this can't be the minimal axiom. It's too big. And so what we do from here, which actually maybe I'll get to it a little later, but the point is that we're going to search for smaller axioms and sort of go from the ground up and sort of see if we can meet halfway. But spoiler is that we've eliminated a lot of axioms, and this is still the best candidate we have, but we know that there are strict bounds on the equational length of a single axiom for rings. Any more questions, or should I go on?
Let's go.
All right, sounds good. So for now, I'm just gonna go through some pictures. These are some of the sort of poster pictures for the project. These are the entailment cones representing the axiomatic systems. So this is the entailment cone of the 7 ring axioms, not including the axiom of the existence of a multiplicative identity. And it's just a directed graph whose vertices are encoded with this information. You can see right here that there are exactly 7 green axioms or green vertices representative of the 7 axioms. And then you can think of the directed edges as being sort of implication arrows, where these orange vertices sort of act like immediate results, first order lemmas, and then the blue ones act as second order results or theorems, however you want to think about it. Immediately below, you can see one that's much simpler in structure, but a lot more dense. And this is the entailment cone of the axiom you saw on the previous slide. So right at the top here, it's hard to see, but there's a little green dot there, and you have these 2 arrows going to this immediate result. So apparently, only one thing immediately follows from that Tarskian axiom we saw. And then you get this massive amount of second order theorems that can be derived from that equation.
It's not one thing follows. It's just a way, one single way of extracting those. You just apply a single substitution in all possible ways of the axiom to itself.
I see. And I didn't actually understand that, so thank you for correcting me. With that being said, though, one thing I was trying to find was the actual information of what is in this orange vertex here, because that could potentially be another candidate for a single axiom for rings. And once again, we see limitations of hardware, because as soon as I try to expand the labels or to go into full form and find what the code actually says, it crashes. And so there's some sort of mystery equation in there that might be another candidate. And that's worth looking into the future. And this one right here, Sorry?
It's just a single inference step. The yellow dot is just represents the actual process of substituting, right? So it's like an event, updating event. That's why I have 2 input edges into that event, and every other edge is the output edges that produces all possible ways those axioms can combine.
Right.
Okay,
So
that makes a
was
lot
gonna-
more sense.
Yeah, that was going to be my question. So if you scroll up a tiny bit in that, so Nick, just to rephrase what you just said, I'm reading the green vertices as the axioms, and then the orange ones are like sort of pairwise combinations.
It's like updating events, right? So those are events that in the mathematics case, it's just substitutions, right? Substitutions, different kind of substitutions of one axiom to another. So we can turn an axiom, because it's an equality, you can turn it into a rule, either left-hand side to right-hand side or other way around. So we already have 2 ways of using the axiom just by directionality. And you can also apply this rule either in one direction or another to itself, also in multiple positions, right? And that's how you can create more axioms out of it, more lemmas. That's why there's so many, because there's just a giant axioms of there are many positions that you can apply it to the rule to itself.
Yeah.
Okay.
And so you always have 2 inputs to each of the orange updating events.
Yeah, one acts as a rule, another acts as a actual expression that you're writing.
Okay, so I was misinterpreting it then. That's really good to hear, because I was searching for this, but it was just a substitution. Okay.
Yeah.
Thank you. Well, in that case,
It's all in the mathematics book by Steven. It's like we explain everything there. There's a lot of pictures like this there.
I see.
Exactly.
I see.
Yeah.
Okay.
So those are basically all the possible entailments of that big axiom with itself, right?
Yeah.
Seems
Just
that
one
way.
step. And imagine you do another step, then each of those green dots produce the same kind of giant cone around it. So it's an explosion, combinatorial explosion.
Yeah.
It sure is. I tried the second order cone, and once again it did crash. So here's another representation of the same cone, just with the substitution a little bit more well outlined. And this is what I mentioned before. This is the proof object of the forward direction of Tarski's proof, but specifically in the case of rings having multiplicative identity elements. I did this by hand as well and used all of the axioms, but apparently you only need 5 of them to actually prove the axiom, which I found quite interesting.
Out of
But-
how many? 7? How many?
But 8 in this case, because we also have that multiplicative identity axiom.
Okay.
So this is the diagram for the proof using the standard axioms to derive that statement.
Yes, exactly.
For rings or groups?
For rings.
Okay.
This one is for rings. So we use the ring axioms along with the existence of 1 to prove that massive axiom you saw before.
Does it use any of the multiplication in this one? I just see minus signs.
I mean, it has to. It definitely does use multiplication.
Doesn't mouse over work? Oh, we turned it
Sorry?
into a.
Yeah, it was to save space. I did turn it into Unicode. Yeah, I can.
It does. Whatever. Well, we have a proof object. You can recreate it if you want.
Exactly. Yes. Yes, you can.
Now, if you want.
Oh, I can. Okay. Let's see.
Just-
Proof. Oops. I got an error. I'm not very good at this. Why is this not working? Hold on. I'm not able to type this in right now. Okay. Proof objects. Is it proof tree?
Proof graph.
Proof graph.
No, it's a like a property. It's just after the proof object, open bracket, and in this and proof graph. Yeah, like that in a string. Or token event proof graph. It looks better.
Okay.
That's the one you'll see. This is a small one, so we can look. Yeah, so we can see immediately the axioms. Yeah, you see, what we're actually proving is the tautology, just an
Right.
identity. So
And
in a way, your hypothesis acts as one of the axioms because it has to be in its past entailment column.
right. And so we do reach this tautology of y equals y. I think I mentioned that, doing that by hand at least. Where's the multiplication though? It could just be these ors. I don't know though. I thought that's a good question to ask because this can't be correct if there's no multiplication in there, because this whole thing relies on both operators. But in any case, I will look into that and hopefully be able to correct whatever is going on there. But anyway, the next portion of the project is where the sort of real meat of it is, and it's actually establishing a lower bound, kind of like what we talked about before. So we have that length 351 equation from before, and now we can use finite models to sort of eliminate candidates for axioms. And we do this by taking potential axioms and comparing the finite models that they generate with the finite models generated by axioms. And if we have a correct axiom, then all of the models should line up for every order. And so if we find models that don't line up, well, that's not a potential candidate for an axiom anymore. So what you see right here is just sort of visual representations of what these finite models are. You can think of them as operation tables. If we run this function, you can see they generate this association of what can essentially be thought of as matrices. This would be a 3x3 matrix, and you can see the circle plus is 0, 1, 2, 1, 2, 0, 2, 0, 1. And you see that in this top left table right there. So that's just a way of visualizing and sort of understanding what these finite models represent. Now, in terms of actually finding possible axioms, we did this based on sort of equational length. So we bound the equational length from below and then eliminates everything. Well, sorry, I misspoke. We bound the equational length and then eliminate every possibility below that equational length and then sort of raise the bounds and then do the same thing. And we can see this sort of function in action, potential ring axioms with two variables on the right-hand side that are two different variables. We can see that it generates quite a few. And we can play around with this, right? We can use 3 variables, and then you'll see C's start to pop up here instead of just B's and A's, which isn't entirely the same thing because we have things like A equals B plus C, whereas we couldn't have 3 variables like that before. We also can change the number of instances of variables and operators like this. But as you can probably see, this ramps up very, very quickly. So one sort of example that we have below is that, well, the next function is one I wrote called equal finite models Q, and it just checks to see whether or not the finite models other than overbar, or the ones produced by overbar, because we've already defined what that overbar is. It's an additive inverse. So it checks to see if the the finite models of two different things are true, or excuse me, if they're equivalent. So we can see, as an example, that taking the inverse of some addition is they do in fact generate the same finite models as each other, and it works for every order. You can check if you want, but if we change this to say something like A, well, it's not, oh, that, wait, hold on. That I shouldn't have made it.
Okay.
Yeah, it's 2. Okay, so it's false, and it'll be false for all orders because they don't generate the same models. Now, that being said, this brings me back to up here. This is why we have this multi-negated option, because it turns out that in every case, the models generated by double inversions will end up being the same, which you can think of it as being sort of analogous to taking 12 equals negative 12. It's a similar concept. So that is to say that setting this option to false, we can see it generates significantly fewer potential axioms, but they keep the same number of possibilities as far as finite models go. And one last,
I disconnected previously. I was just going to comment that we also can canonicalize the names, right? Especially when you have free variables. If you just have A and C in the equation, you can always rename C to B, right? So that
right.
it's not the same. So we can
Yeah,
drop a
and
line like that.
a similar, that's also why you only see equations starting with A right here, because if you had all of the permutations of A and B, then you're going to get equations that are just same up to renaming of the variables. And so I'm glad you pointed that out. That is another way we sort of decrease the number of potential axioms that we're looking at. So just as a sort of silly example, this is A equals B plus B. Is that equivalent to the ring axioms, including the existence of multiplicative identity element? Of course it's not. We get false there. And so that's the idea, is we take some set of potential axioms, we take this equal finite models, we run it over that list, and so far everything we've gotten turns up false. And so
Or shouldn't you check for, not for equality, but like for inclusion, right? You have a general, like you have all the axioms, right? They generate some models. But if your model, smaller axiom, generates just more models, that's still okay, because you're allowed to add more, right? You just need to have that they all satisfied. So not same queue, but at least like a intersection. Not the intersection, it contains all. So all the models of your small axioms. Yeah, so your small axiom models should contain all the models of your actual ring axioms that you have, right?
Right, but wouldn't we want the ring axioms to also be contained within the single axiom? Because they're supposed to be sort of encoding the same information, right?
Well, not the same, but they should be basically by adding more axioms. You just you filtering out the models, right?
Right. So what we're doing here isn't necessarily trying to find a sort of like, okay, well, this contains like half of the same finite models that the ring models generates, but it's to find an equation that generates the same ones, because we have a single axiom system, right? We already have one, and so we're looking for one that's smaller. And so if we find something that's smaller but two different axioms, then that's a bit less desirable. And I don't think I mentioned that at the start, but we sort of value the number of equations much more than we value the actual length of them as far as minimizing axioms go.
I didn't quite get that. What are you saying?
Well, I guess I'm trying to say that What am I saying? I'm not understanding why an inclusion would be enough, because I'm not trying to find, say, 2 axioms that satisfy the ring axioms. I'm trying to find just one. And so if I have if I have finite models where one set of finite models is contained within another set of finite models, then I don't know why that's enough, because
Well,
that's not.
it's not enough, but at least it's like an indicator. Like, okay, this is like, if it includes all the axioms, but but has some extra models that doesn't coincide with an actual ring axioms, right? You can at least go, okay, this is a good axiom. Maybe I can add more than would restrict it, right?
Mm,
But maybe you can also say, maybe I don't have to add one, but maybe I just have to modify it a little bit.
okay.
Right.
No, that's a great point you make then. Yeah, I think that'll be worth exploring in the future then, because this is a pretty easily modifiable function. So I suppose that if you find inclusions, that it would be easier to restrict the search to more similar
Yeah.
equations. Okay. Yeah, that's a great idea.
You can be very creative there. You just start like, it would be like your fitness function. You can do adaptive evolution of your axioms, right?
Okay.
You just check the models whether they include it or not. That's if they all include it, that's a good one, and they just perturb them a little bit. Maybe you can derive the axiom this way.
Yeah, that's a great idea. I never even thought of that. So even though we have this great idea now, I did not during my work in the project so far. And so the main approach I made was this one, and it's, as you can see, pretty brute force. And so there's only so far you can go with brute force, but we have gone to equations having a length of 11. And when I say that, I mean that we tested equations that were length greater or at least 9. So we tested every single possible equation having length less than 11. Because I guess one thing you can think of is that if you have, say, A plus A equals B, something like that, you're always going to have an equals, and you're always going to have variables separated by operators. And so assuming you don't have any inverses, it's always going to be an odd number, and adding inverses would only increase that number. So the point that I'm making here is that if we test the sort of potential ring axioms generating function that we find here, we're only going to have, say, in this case, systems that are, or equations that have length 5 or more. And if we test it for 3 variables, we'll have 7 or more. So we didn't find any equation that generates the same finite models as rings do, not even at the second order, for any equation having 9, or excuse me, 11 fewer than 11 variables. So we have an upper bound and we have a lower bound, but we don't yet have an actual provably minimal axiom. Another path I sort of went down during this project was to use McCune's group axiom and to try to sort of make a 2 axiom system for rings using the very convenient group axiom, and then sort of trying to use just our logical thinking to sort of combine the left and right associated or distributive axioms with the associative axiom with multiplication. But I didn't get very far in that. And so you can see here, that's the entailment cone for the abelian group axiom, in addition to the 3 multiplicative axioms that you saw at the very start of the presentation. But the main result is that we have upper and lower bounds on the equational length for rings for a single axiom system. Are there any questions there?
So this is setting a lower bound. essentially?
Yeah.
Uh-huh.
That's kind of what we were doing with those finite models. Is we're showing with that potential ring axiom function that these are all of the possible equations that generate different finite models. And we check all of them, they don't work. And so we
You
move
have
to
to
the next.
actually, all your axioms should always include all the operators that you have, right?
Well, sure, but earlier in the project, I didn't include this in the presentation, but up to the indices, I was finding that they generated the same finite models with or without axioms. Or is that
Oh.
generally incorrect?
Well, I don't know. I meant that you have to generate axioms that contain all the operators of the ring axiom, right? Not just plus and minus. So you already
Right.
have some lower bound if you just do the minimal composition, like plus multiplies multiply negation, like 3 variables equals 4 variables. So four variables is already a low bound. I guess it's just like the easiest way to cram all the operators into a single formula, right?
Yeah.
And generating, so yeah.
No, you're right. You're right. I mean, the result makes sense, right? Because we also have that rings are abelian groups, and we know the length of the abelian group axiom to be greater than 11. And so it's not necessarily a very notable result, but it is a bound regardless. And like I had mentioned before, it was very limited by this brute force approach as far as the hardware goes. And so there are a couple things that could be improved. Like when you get to sort of higher variables and higher number of variable counts, there are some sort of equations that do generate the same finite models despite the restrictions we put on it. And so there are still ways to improve this and to sort of hopefully be able to expand this bound. But I'm not quite there yet. One other thing I will say is that in McCune's paper on the group theory axiom, there are some bounds in the, wait, what if we rent, sorry, I just saw the chat question. What if we rent some compute? Any idea what scale we need? I hadn't considered it. I don't know. It's a good question though.
Yeah, in the past we've rented compute from AWS and run some things on their servers. So if the scale is within a reason for that sort of context, then we might be able to send a job out and check the result there.
I see. I would probably want to optimize the code a little bit more before actually trying anything of the sort. But that's a good idea. I'd never even thought of it. But as far as sorry?
Have you actually succeeded to derive models up to how much, up to what size you derive the models for the actual ring axioms for those 7 and 8 ones?
I don't recall. I think that I could easily do 4, and that 5 was a bit tough, but possible, and that 6 just wouldn't work.
Well, you don't have to go high unless you find at least one that satisfies 2 first, right? If you find one axiom that satisfies models, works for model size of 2, then it's better. Then you just check higher
Right.
sizes.
So that is what we did for this lower bound, is that we didn't find a single axiom that worked with even the size 2 finite models. And so we try a size 2, it doesn't work, we move on. So that was the approach. And so the hope was that we would find at least one size 2 that would be true. And then we could sort of explore that one further. But every single axiom we checked came up false. And that's pretty much all I have for you today. So thanks for having me on. And I mean, we've had a few questions already, but if there are more, then I'm happy to talk about it, and I'm happy to talk about this further in the future if anyone is interested.
Yeah, it's
Any
really
questions
interesting.
on YouTube?
What was that, James?
No, I was just checking if there were any questions in chat on YouTube.
No, we are good.
Yeah, that was really interesting. Thanks, Tate. This was a fantastic exploration.
I appreciate it. And thanks for having me on. And also, I appreciate all of you for asking me all of those questions. It definitely clarified things for me as well. So I appreciate it. Thank you so much.
Absolutely.
Well, thank you very much, Tate.
Right. Have a good rest of your day.
You as well.
You too.
A nice one.
All right.
Bye.
Take